Hello, everyone, and thank you for joining us today. Welcome to Megger's Virtual Relay BPS. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as one of the moderators for today's presentations and supporting you on any technical issues or questions for our presenter. Oh, David, would you mind switching over the slides so I can show them the Q&A? Thank you. So on the bottom of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing the box highlighted in red, and I'll read the questions out during the Q&A segment at the end of each presentation. Today, we will have two separate presentations with their own Q&A sessions, so please stick around after our first presentation concludes. Our presenter for the first segment today is David Beard, Relay Applications Engineer with our Technical Support Group. Also, to assist with the question and answer session, we will have three panelists joining us today. Today, we have from our Protective Relay Department, Mohit Sharma, Applications Engineer, Marius Pitzer, Product Manager, and Sugosh Kuber, Applications Engineer. Okay, let's go ahead and get started. Thank you for joining us today, David.
Yeah, thanks, Mike. Okay, today we're going to go over best practices for, it's like a best practices seminar, just kind of giving you guys a feel about some overcurrent elements, frequency testing, today using RTMS, and just a little bit of basic background as well. What we would like to cover in this agenda is just a little bit of overcurrent protection. What is it? Time current curves, which we see a lot of throughout relay testing, and not only just overcurrents, but other scenarios. We're going to explain those. Overcurrent coordination a little bit. What is frequency elements? And testing with relay test management software. Okay, so first overcurrent relay was actually designed around 1904, and it was produced in 1905 by a company that is now known as ABB. It is one of the oldest protection systems that's actually stood the test of time, and it's not to be confused with overload protection. Now, overload protection is a running overcurrent that would actually cause overheating of the protected equipment. So an overload is actually a type of overcurrent, but overload protection typically operates on an inverse time curve, where the tripping time becomes less as the current increases, and we will see that again. We'll see that actually in the future slides that we have here as well. So the main purpose of overcurrent is to actually clear the fault. That's our main objective with overcurrents. This protection is against excessive currents, and we want to make sure that the current does not go beyond the acceptable current rating of the equipment that is protecting as well. So it generally operates instantaneously, or we have some type of time delay to coordinate the different types of faults depending on where they are in the system. Let's see, we also have, it's an inexpensive application to apply, and also it's very simple to set up and test, so it doesn't really take much to actually test an overcurrent. It's just getting the idea down. Now, these are different types of overcurrent devices. These devices will protect against current faults, and now that they perform this type of protection, it will be different for every type, but the overall principle is the same. They're still protecting the device for some type of overcurrent condition. The first one that you have is a molded case breaker, and it uses a bimetal element that is heated with a load current. So when an overload or a short circuit occurs, the bimetal inside the molded case breaker flexes and kicks the breaker off a latch. And then so it actually breaks the circuit inside the molded case breaker device and the housing. We have a few arc chutes and some other options, or not options, but other ways that it's made internally, but we're not going to go over those. But it is a trip-free device, and that is nice as something to know, because you can't just simply hold the handle and prevent it from tripping, like I've seen people do with some lockout relays years ago. So the next device is actually a fuse. So it uses a fusible link, and the fuse actually senses the fault the fault condition, and the internal fuse link will actually melt by opening the loaded circuit. The link will also be blown clear of the insulator housing, and if you've ever put one of these inside, if you ever tried to put a fuse back into service while the actual fault is still there, then it's very loud. It is a loud blast, and definitely have to be protecting yourself. And then the third thing we have is electromechanical relay. And what this guy does is he actually senses fault condition by using CTs, or current transformers, that are either coming from a breaker transformer or even some external CTs that are actually in the yard. So when the predefined setting of the overcurrent relay is exceeded by the tap value, then we'll actually, the disc will move and it'll close a set of contacts, which will actually attach to the circuit breaker trip circuit. And therefore it'll open the associated breaker that's actually tied to the trip contacts of the electromechanical relay. Okay, we have a few different types here. We have some solid state microprocessor based style of relays. We also have solid state relays. We also have electromechanical relays. And then we also have some circuit breaker auxiliary trip devices. And in general, the idea is that they all protect for overcurrent fault conditions. So they're all doing the same type of function. And whenever they're doing this function, it doesn't matter how they get there and how it works out, whether it be in a new microprocessor base or it's actually an old electromechanical, the concept is pretty much the same. They are going to open for overcurrent fault types. Okay, so these, so the different styles of overcurrent can be broken up into these different times or different types. One you can classify as the definite time, inverse time, or inverse time with instantaneous. Now, the definite time allows engineers to adjust the time in fixed steps with the breaker closest to the fault, and it will be tripped in the shortest amount of time. So we're just giving it a short, a consistent time over multiples of current. So it doesn't matter what the current level gets to, the time that it's actually going to trip will be the same. The inverse time idea is that it will operate in a time that is inversely proportional to the fault current. So the advantage of this is that the current magnitudes will increase in time in which the relay will operate will decrease. And we'll actually step through the inverse time characteristic a little bit more later on, and we'll kind of really dial in to how we can pick our points over different current multiples. The instantaneous element that's actually tied into the inverse time characteristic as well are very effective in reducing operate times of severe faults. They don't offer any selectivity because they do have different characteristics, and two, they're instantaneous, and they're instantaneous for a reason, because we want to make sure that we get the fault current off of the relay. We want to get the fault current off the device in the yard as quickly as possible to minimize damage. So ANSI an IEEE standard C37.2 is actually a device number device function numbers. Sorry about that. So for the instantaneous level, it's actually for a 50 element, and we'll go through each one. Will actually have its own IEEE number as well. And the instantaneous, again, means no intentional time delay. And when the current has exceeded a predefined protection setting, then we want it to operate in the shortest amount of time possible. Usually you'll see the 50 element with phase. You'll see it with neutral, and you'll also see an instantaneous ground element as well. The instantaneouses have high or low current settings. So it doesn't, just because it says instantaneous does not necessarily mean that the current value that it's going to operate has to be extremely high. It can be a very low value. So here's an example of what of how the instantaneous overcurrent will work. So you'll have a time over current, and you'll have some pickup value. You always have to have some predefined pickup value that will be set from engineering after they've done some load studies and so forth. But the idea is that if I had a fault current that comes into the instantaneous area, then we're going to immediately trip. All right. So let's say we added a 0.6 second delay into the instantaneous. So now what will end up happening is our operate region has changed, because now we have to wait for this timer to expire before we can actually get into the operate region in our instantaneous level. So this is with an intentional delay that could be put in for coordination reasons. It could be for wanting to run equipment a little bit longer. But again, this is a setting that actually gets placed into instantaneous values only by engineering staff. Now, let's go to the next one. So, and again, we'll come back even on this for the instantaneous level. Again, it's a very simple concept. It's either, if it gets above a certain threshold, it actually operates. If it doesn't get above the threshold, it will not operate. It's very easy to test, and we'll actually test in the instantaneous level here at the end of this seminar. So the time over current. So a little bit about time over current is that the ANSI IEEE device number will be 51 element. So every time that you see a 51 from here on out, we're going to be referring it to time over current. Then we're going to get, every time the 51 element will have curve selections. So we have multiple curve selections inside of the relays themselves. So we have a wide selectable range, and we'll kind of talk a little bit about that too, just kind of the different inverse times. And we'll also talk about the different time dials and so forth, so we can actually get in here. The different time dials, the minimum pickup setting, we will go over as well. And then usually we will see the 51 element associated with the phase, the neutral, or the ground elements. And most of the 51 elements will have some type of TCC, and most of them will have either an equation tied to those, or you'll actually see the older electromechanical style where they have, they used to call them the old skins. They're really thin pieces of paper. They had the graph, the logarithmic graph on them, and then whenever you go through there, you would have to use your little ruler and a pencil. So it was enjoyable to kind of walk through that one time in a career. So the time over current, the TCC, what we from here on out will be called the relay characteristics. You can see that there's some standards. There's standard ANSI, there's IEC, IEEE standards, and this is just an example of a few, and how the calculations are derived. So these are in all of the manufacturers' specifications. So if not most, if not all relay manufacturers will have the TCC curve calculations listed in their manuals. Also, they do provide some custom settings as well. So it'll allow you to derive your own custom time current curve as well, if you seem fit to do that. So time over, so on this, with the inverse time region, this is going to be an I'm kind of show you a little bit. So you would have again, time over current reference, and we would have some pickup value, right? So we also have this operate region. So anything above our TCC or our curve that we have selected, anything above outside of that curve time, we're actually going to get into operate. So if we were to come in here and say a fault was played our fault actually happened at this point. Once it gets into, this will be the non-operate region, and this will be an operate region. So after our time has expired from the time current curve, then we would actually be into the operate region, which we should see an operation. And the operations usually happen right on the line with the plus or minus of percentage listed by the relay manufacturer as well. And if we were to actually try to capture this time here, what we're going to do is, as we're testing, we will actually provide specific current multiples along this graph to allow us to see the difference in time. So as you can see, the least amount of current will actually provide us a longer time, and the higher amount of current will provide us a short amount of time, which makes it an inverse style curve. Okay, so here's a good example. So we would have a, let's say for this instance, we're going to do a tap of 5 amps, right, for your tap. And then also we have a time dial of 3, or a time multiple setting. And what we're going to end up doing is we're going to take this tap value here, and we're actually going to multiply it by the current multiple. Now, if you see on this graph, we also have the time in seconds or cycles. A lot of times you'll have seconds on one side and you'll have cycles on the other. And then also we're going to have a multiple of taps. So this will be a multiple of our tap setting that we're going to actually use to be able to find the time that's inversely proportional to current on this graph. So if we came in here, first thing we need to do is we also need to know what time dial we're on. So for this one, I just plotted one graph on here for one time dial. I labeled it as number 3. And what we're going to choose for our multiple is we're actually going to use 2. And in order to find this, you can start from one end, go to the right, from left to right, but also try to start a little bit closer to the curve itself. You don't want to start way over here. You want to kind of get closer to where the curve actually makes the mark, because if you start way over here, it'll take so much time for this curve, if it even crosses into the smaller multiples of one setting. And if it does cross over there, then there's probably something wrong with your settings, or wrong with the relay as well. So we're going to do a 2 times multiple, and we're going to follow this line all the way up. And sometimes it's a little difficult to do it on a PC. A lot of times you can do it with a ruler. And then we also want to come over and see what that time is going to be. So we think that we're somewhere around 5.8 seconds. So we would have 1, we'll do 2, 3, 4, 5, and almost 6. So I would say somewhere around 5.8, 5.7, and maybe 5.9. Who knows? It's just kind of, it's a little bit in there. And again, it depends on how big your piece of paper is. It depends on a lot of things, but in relays that actually has specified, they have specific equations for the time current curve, these numbers are almost pretty spot on. And yeah, so what we'll do is we come in here, we'll also have the 10 amps applied, because we're actually going to do a tap of 5. We're going to come down here to a multiple of 2. Right, so we're going to apply 10 amps, and the relay is going to operate somewhere in the 5.8 second range, give or take. And that give or take is actually going to be your tolerance levels that are actually on your relay as well. So in this example here, what I like to show is, so we just showed that if we did 2 times multiple, we would have one. We would have one time, 5.8 seconds. So in this one, we have multiple time current curves here, and these are all could be time dials, right? So we could go from half time dial 1, 2, 3, all the way up to however many time dials or time multiplier settings that the relay could have. So let's say if we use 2, so we're still using the 2 multiple, which crosses all of the actual time dials curves or time dial setting. Then let's say we reach this point. So we're going to pick this curve out. So let's say this is time dial 1, just for just for simplicity. And let's say it crosses the line at 2 times. When it crosses over at 2 times multiple, then we might get 1.5, approximately 1.5 seconds out of it. So let's say if we picked a different curve on applying the same amount of current, then we could very well get a different time. We can actually get a longer time. If we came down here to this halftime dial or this lower setting, we could actually get a faster time. So when you look at the curves, we could have a continuous, a constant current value with multiple times, or we could also have one time with multiple currents. So I didn't draw this out, but let's say if we had something at the 0.5 mark here and we wanted to keep it 0.5, we would come all the way across. This first time dial would hit us at 2 times the current value, but then if we hit 0.5, we might not even get across it until we almost get a little bit after 3 times the current multiple. And with that, that just means that we can actually still apply a specific time, but the current level might be a little different. It's going to be increased, actually. So it depends on where you want to go within the curves, but the actual inverse curve works the same way, whether we're using constant time or we're using constant current multiple. Okay, so in this one, we have a little bit of the TIC, which is the time coordination interval. We'll speak a little bit about this. It's basically a minimum time between operating characteristics of 2 series devices. And what we mean by series is that, let's say they're on the same circuit, okay? There's factors that can influence this time here. And what they can be is the breaker fault interrupting time, because one breaker operates different in summer than it does in winter. It could be one model of breaker on one end of the feeder versus a different model breaker. So there's a little bit of flexibility in everything. So when you look at the system as a whole, you have a lot of small errors that need to be added up so you can actually get this TCI or this correction factor here. You can actually get this guy pretty close, but you're never going to get it exact. So the safety margin is to calculate for safety margins within different devices can play a role as well with calculations. Relay tap selections. So let's say you have a microprocessor relay on one breaker, and then the second breaker downstream is actually a electromechanical relay. So you're going to have a little bit of a error there as well. The relay operate times. Some relays operate faster than others, especially if you don't have the same brand or same tile or same type of relay in series. And also you have CT ratio errors as well that do play a role in this. So we're also so some basic rules for coordination is we're going to use, it'd be nice to use the relays with the same operating characteristic if possible. It is important because the job of coordinating all these devices, and let's say that radial feeder I was talking about, is a challenge in itself. So you don't need any extra help, right? So if each relay has a different characteristic, and the task of coordinating the operating times can be a nightmare as well. So if you kind of look, or where am I going? So if you have the farthest relay from the source, so if we're looking at the farthest relay from the source, we want to make sure that the current settings are equal to or less than the relay behind it. And what this means is if you have a relay that's at the end of the radial feeder that we're talking about as well, and the current setting is more than the relay closer to the generating source, then you can guess which relay will operate first, right? So the relay behind the one with the higher setting will actually operate before the one that we need to operate. And it's very similar to these two cars, right? So if you look at the two cars, you can tell, can you even tell which one is in front or behind? you can't tell who's in front and who's behind, who's passing who, right? So if you follow the basic rules for coordinating your protection, then you'll set that precedence. So you'll set the precedence of which relay is going to operate first and which one operate first when the fault occurs in the system. And then of course we have time and current as well is a very important. It's a foundation in which the overcurrent relay is developed on. So let's go next. All right, so in the coordination example, we're going to line out a couple of examples here. So the first one is we'll actually throw in a fuse. We actually have a fuse damage curve here. We also have our normal feeder that we had earlier in our main. Still, again, inverse time over current. So we still have the same, we're still talking about the same current, same TCC. We're still talking about the same style of inverse curve. And what we're going to do is we need to make sure that our fuse coordinates with the main breaker or with our feeder breaker, right? Because if our feeder breaker actually operates before our fuse melts, then there was no point in even having the fuse there anyway. And two, you're actually going to take out more customers than you need to. And it's really a good rule of thumb to kind of give. There's multiple good literature, good experience. I would highly recommend talking to your peers, especially when you're trying to coordinate devices, because usually some have 2 to 5 seconds or 0.2 to 0.5 seconds for coordination between inverse curves and fuses, or you might have between 3 and 6. So each utility, each spot has its own method and what they use to coordinate this time and how much time they want in between each device as well. So then also what we do need to look at too is we need to look at the coordination between the two relays. Not only the fuse, we don't want to stop here, but we also want to make sure that we're actually coordinating between the two feeder, the main feeder and our regular feeders. And usually we want to shorten that time just a little bit because they do operate faster than having anything melt down, kind of like a fuse would, since that's a one-shot go around there. Okay, in this example, what we have here is we're going to try to point out what our problem is. So in this one, we have a substantial problem, actually. So let's just walk through it for a second. So we do have our coordination between our inverse time characteristic on feeder, on the first feeder or a feeder. We also have our fuse, and we have a good coordinating time in between here. So we know that we're not, if our feeder needs to operate, it's not going to operate the fuse, and vice versa. The fuse is going to go before the breaker only if the fault is closer to the fuse. Now, here is our problem. Our problem is we have our main breaker. If this current level comes up where fault number 2 is, then we're actually going to operate the main breaker before we operate our feeder. And that's not good. That just means that we took out a good portion of either customers or some type of industrial process. And somebody's going to be looking for a job after that one. So what we want to do is we need to fix this issue here. And how do we plan on doing that? Well, what we need to do is make sure that we go back to our the main breaker and feeder time current curves. We need to adjust the settings, and we need these settings and also the curves to determine who needs to trip when. Right? So we need to establish the precedence like we were talking about earlier. So by using the information that's given to engineering from fault studies, various simulations that were performed using software, we can better protect the system and minimize the amount of customers that can be affected during an outage, because we definitely don't want to take out any more people than we have to, or processes, because a lot of processes are cannot be stopped. Okay, so as we know now that overcurrent protection is essential to the power system, and you know why. We see why that the coordination is key, and with properly set overcurrent elements, we should be able to see the difference between clearing the fault of a few customers versus the whole city. And now we're going to start into the frequency elements. So in an IEEE standard C37117, it states a change in a power demand or in production causes a fluctuation of the speed of the turbine generator, resulting in fluctuation of the frequency of the power system. So what did we say? We said frequency elements are here to detect, their purpose is to detect the power imbalance conditions on the power system, right? So can we have a definite time or some type of time inverse curve? We sure can, because microprocessor and solid state relays, they do give you a definite time basis, but also the older electromechanicals, for example, like a CF-1, it's an old Westinghouse relay, actually still has the time current curve disk, the same induction disk. I say time current curve, which is not right, but it still has the same disk method, and also it has time dials, and they can be used. So these frequency relays can be used for grid frequency fluctuation. What if a machine actually starts to run away, or we have some controls that are the governor controls are not operating properly, or we could also have the automatic voltage regulator, or what we'll call now as the AVR, could fail as well. And when the AVR fails, the generator starts drawing reactive power from the grid, and now the generator is an induction machine. So it's operating above synchronous speeds. So we can have an over frequency situation, or we can also have an under frequency situation. And this will bring the generator out of sync as well. So we definitely don't want to damage the turbine, since it is the main piece of the system that keeps everything going is the generator. We can have multiple stages set. We can have multiple frequencies. Some relays offer six different stages of settings. We can do them all for under voltage and do them all for over. You can do a mix match of either one. And it's also very simple to set up and test as well. So these are a few types of frequency style relays. We can have a little newer microprocessor based, comes in different shapes and sizes. We have that old CF1 there. You know, I think they're still in service today. I have tested a few of these old guys years ago. And then we also have the old static relay, which is GE, and these guys are still around as well. And then even some manufacturers are putting out their own load shedding relay, which is just specific for that particular application. So in general, the frequency element can be placed in, can come in all shapes or sizes, actually. Okay, so frequency is a reliable indicator of an overload condition. So the frequency relays are either over or under, or they can be both. So a relay can have both settings. What they also help protect, they protect the generators from damage. They're protecting for the system. We want to make sure that everybody still has power, can still do things. We definitely don't want hospitals going down. We don't want industrial plants going down, and we definitely have to make sure that we protect the generators from frequency issues. Serious damage can actually result from if the frequency settings are set outside of the specific limits of the equipment. So it's real key to actually make sure that we're coordinating even the frequency elements as well. And then when a major generator drops offline, So if we have one that actually, I think there was some blackouts that everybody's heard of that's happened over the years. When one drops offline, it's not good. Of course, it becomes this cascading effect. And with frequency relays, this will help mitigate these by specifying which breakers to drop out from load, so we can still maintain some type of system stability, and then we will add load as we go to get us back up to where we were before the fault occurred, or whatever that instance was. But the overloads can plunge the system into a total shutdown as well. Over frequency is mainly used for overspeed protection. And the under frequencies can be used for multiple items. I'll discuss here a little bit about load shedding. We won't get into a huge big topic about it because it could take another webinar for this. But what we're trying to do is just kind of get an idea of what under frequency load shedding is. We want to get the general idea. Okay, so what we're going to do is, if you look at the diagram here, we have a supply side, right? Let me use this guy. So we have the supply, right? This is everybody, generators. This could be wind farms. It could be, any type of solar farm, whatever. Anything that's generating electrical power to the grid is actually part of the supply, right? So when you come over here, we also have demand, which is us. It's the consumers, it's the industrial plants, it's the people using electricity, it's manufacturing plants, it's whatever. Anything that we have actually is pulling from the grid. So what we want to do is we want to keep this balanced, right? And in order to keep this balanced, we have to have the demand has to be equal to the supply, right? And as long as we don't get too far out of balance, then we're able to maintain the system stability. Now, once we start getting out of balance, that's when we start having a lot of issues. We start having issues with cascading effect. We have to start shedding load. We have to start getting everything figured out. And so let's just put this up there. So what if the supply went out? So if all the supply is gone, if one generator section just goes down, then, and we're accounting for that load to be on the system, for that generator to pull its load, supply the load that's requested, and that generator goes down, then the demand is still there. This demand is not going anywhere. It just gets bigger. And why does it get bigger? Well, it's the same load, right? But we lost the supply. So the demand is now more than the other generators can handle, because now there's not this one generator pulling its weight anymore. He just left the game. I mean, he's out. And then now the load, all the people are still there, so the load is still there. So for an example of a load shedding event, so let's say that the frequency might get down to 59.6 hertz. So that could be the first level in which we actually dump a percentage of load that's on the system. And if our frequency continues to keep dropping, then let's say we get down to 59 hertz for here in the States. If we get down to 59 hertz, then it could very well drop again, and we're going to have to shed some more load. So, and if we don't continually shed load to keep our generator online, what ends up happening is our generator goes under frequency. So we have a trip. We open the connecting breaker out in the substation. It connects us to the grid. We become unsynchronized to the grid. And then now our generator breaker is opening, and then we have to get everything back up to where it was. But even at that point, we can't do that because we still got to shed some of the demand. We need to make this demand smaller. All right. So under frequency load shedding, what we do is, mainly it's large industrial customers. They consume a good portion of the power in the power system. They use a lot of energy, and what we try to do is they come up with a some type of I can't even think of it now. I was going to say lease or some type of program to where the industrial customer will get a specific rate, and they get a good energy rate to have this under frequency load shed protection placed on certain substations in their group where they're bringing power in from transmission lines or some other feed or source that they have. So they do get pretty good rates for that as well. In order to prevent the under frequency load shedding, the utilities are constantly monitoring loads. They have to monitor the load daily. They're monitoring it minute by minute, second by second. They're constantly monitoring this metering, monitoring the load, not the metering, load. And then they also have to prepare to coordinate when adding other devices. So other power sources or types of generation, especially when you're trying to bring on a bank of wind farms or you're trying to bring on more solar farms. Just because they're out there, they have to be able to accommodate for those extra loads being put on there. And then too, during load shedding, we have to start balancing the system. What needs to go off, what needs to come on, and so forth. So there's a lot of people behind the scenes that actually do this. Okay, in summary, what we want to do is we all know that overcurrent devices are necessary to protect the power system from faults, right? And then when we just looked at the time current curves, they're very simple to read. It didn't take us much to read how much multiple do we have to what the time is going to be. So we'll see a little bit of that while we're doing our testing as well. And then the relay manufacturers always have the same standard. They go by specific standards, but also, like I was saying earlier, is that they also provide custom settings. So you can customly create your some type of inverse time curve in case the ones that they have for you are not reasonable enough for you to use for your coordination. And then frequency elements will provide the protection to keep the power system fluctuations to a minimum, but two, we're always constantly monitoring and we're looking at the balancing of the load and the load and what our supply is. Under frequency load shedding is a good helpful tool for utilities because it allows them to shed the load of big industrial customers and in customers who are they're consuming large amounts of power as well. And then to set up and test these, you're fixing to see this, so that's no big deal there. All right, so we're going to get into relay test management software. And before we're going to actually jump into this, I got a quick note. I got to tell you what I'm using, so we need to know how we're going to do our tests, what kind of tests that we're using. And today I'm going to be using the SMRT 46D, which is the one that it is set here. We also have multiple SMRT units as well. At the top, we come down from the single phase unit to our 10 current unit, and then we also have display model versions, and then we also have the Spheriker down here. He's a really good test set as well. Can still perform the time current curve functions that we're doing here. Frequency, we can do a lot of testing with any of these types of devices. And let's get started with what I'm going to test. All right, so I took a picture of the relay I have here sitting on the bench, right? So we're gonna jump on this 351S, kind of give you guys a little look at my settings here. We're not gonna have a huge amount of time to go through each individual test, but we are gonna try to at least hit the pickups and at least hit the time current curve for the phase. And then we also want to hit some of the tests for the frequency when we do a frequency pickup along with a time delay. And then I need to give some parameters of what the system is going to be like. So our nominal voltage here is set for 66.4, and then our frequency here, since we're in states, is going to be 60 hertz. Okay. Here's a look at my setup. Since everybody, I'm assuming a lot of people are working from home or kind of looking around, so it's kind of excuse the little pictures here, but you know, a lot of this stuff is pretty simple to do. I'm doing it at the house. I'm not saying test relays at the house, but you can do some testing if you need to. The top of my 46D here, showing you that I'm using these dedicated current channels. This number 1 I'm labeled as my A phase, B phase, and C phase. Also have B phase will be my yellow, and C phase will be blue. We also have to have our binary input because we need to sense the contact that's coming from the relay, because we need to know when the relay is going to operate in order for us to stop our test set. And this side, we also have our relay, which is the back, and how I have this wired. A phase again for our currents here. We'll match B phase currents as I have here. And then also C phase current here. We're also doing C phase current here. And then the voltages follow right behind it, right? So the same color voltages, red for A phase, yellow for B phase, and C for is blue. And then we have our return for our neutral on our voltage as well. And our binary input, I have it tied here to out 107. So we're going to use that. And all right, it's showtime. Okay. So this is RTMS. This is Relay Test Management Software, and this is what we're going to use today to actually perform the test on this 351 relay. And we're going to test the ones that I have the settings for that I showed you in the past 2 slides. So I want to give you a quick look of what we're doing here. So this is our settings. We need some type of setting. We need to know what these settings are. We need to know, you can't just blindly go up to a relay and start testing and not have the information from the relay or from a setting sheet or something that's given to the technician. So you have to have something to go off of. So what we're going to do is we've listed here, we have a few settings enabled. I'm going to go to my 50 elements. So all these settings were brought in from this relay, and we show our 51 P1P, we show our 51 ANDs, and we also show the 50G. Sorry, I said 51. It's actually a 50, and then our 50G 1P as well. So these settings are actually read from the relay and brought in to RTMS program in our settings tab, or our settings area here. Okay, so we're going to come into our test, and these tests I pre-created, created beforehand, tied settings to. If you guys would like an overview or some type of demonstration on how to do this, let us know. We will be more than happy to walk you through it and help you create test plans that are very similar to what you are seeing here today as well. So I'm going to start with this 50P element. So I've actually created this test and named it the 50P1 pickup test. And I'll go into this test and kind of give you an explanation of what we're doing. So inside this test, this is how we're actually going to perform this test. So we need to set up how, the parameters. We need the how, what, and when, right? So we need, how are we going to do this test? Well, we're going to do it with a stair ramp, or not stair ramp, pulse ramp. So we have the pulse ramp selected here, and you can see all of the information that I have predefined into my pulse ramp. So we have a pre-fault time. We're going to have a 90% of our start value is where we're going to start. And then also we have our steps. And I did speed the step up a little bit. You can change these to whatever makes you comfortable, however you want to run the test. But we are, if you do notice, we are running a pulse test. We're running a pulse ramp because it is a 50 element. A 50 element is what? Couldn't hear you say it, but I can't hear anybody anyway. So a 50 element is instantaneous, right? So what we want to do is we want to go ahead and pulse the current for just a small duration of time. We want to turn it off, or not really turn the test off, but don't pulse anything, increment that value and pulse it again for another value. So we're going to increment at 0.1 every time the test set comes on and goes off. We're going to increment up 0.1. Then we're going to go again 0.1. And you'll see that here in a minute. Also, we have to have some type of stopping value. So we can't just let this thing run all day long and let it just keep going. We have to stop it because at some point you have to decide, well, is the relay going to work? Is it the test messed up? You know, what's happening? And so we need to go ahead and set that parameter. 2, we need to know what are we going to run. So here's A phase. So I have A phase selected, which is I1. And we saw that earlier on my connection for my test set that I chose I1 as A phase, I2 as B phase, and I3 as C phase. Okay. Now I have selected multiple ramps in here. We have 7 ramps. It'll walk through these pretty quickly. The first ramp I have created for A phase, B phase, C phase ramp. 4th one is A to B, B to C, C to A ramp, and then a 3-phase ramp. Okay, and each one of these will be a little different. I will show you the A to B. So we're actually showing 2 currents here, A to B, 180 degrees out, and then we're also doing the same parameters, right? Because the 50 element is the same whether I do phase, phase to phase, or single phase. No, wait, 3-phase, single phase, phase to phase values. And then now we need to know the what? So the expected value. So this expected value is the setting that I pulled from the settings that you saw earlier. So now we're going to run this test. I'm going to come back to 1. Just so everything looks cool. We're going to hit play. And now I'm actually running my test set. You can probably hear the nice test set operation happening. And again, you're seeing here, see how the increment in the pulse? So as I look at 3, this will be my C phase. You'll notice that this is actually pulsing. So it looks like it's ramping, it's incrementing up the value, but actually what it's doing is it's pulsing it on for your 10 cycle delay on and 20 cycles off. So each one is actually working. Okay. Don't think this guy went crazy on me, did he? Oh, something's wrong with my output. That would happen right now, would it? Okay, I'm gonna stop this test for a second. Sorry, gentlemen, ladies and gentlemen, everybody on the screen. I'm making sure my was working good for a second and everything went crazy. Sorry, I'm just doing some troubleshooting. What we have to do in the field sometimes to figure out connections and what's happening. All right, everything looks good. So let's rerun that dude. Okay. So it doesn't like me today. So what we're going to do is we're going to move on. We'll go to the next one. Let me try this guy right here. Let me get, sorry about that. I'm going to change connections a little bit. Let's run this pickup test. Okay. Apologize for that, guys. So what we might do here is we might go ahead and I got a few things going on my connections. I think my table was bumped a little bit. I should and see what's killing me. This real life scenario right here. I'm telling you, this is how it normally goes in the field, right? So this pickup value, okay. So we'll run this timing test. Yeah, it's not gonna work that way. Okay. Well, showing you for the test. Okay, so I have something going on here. What I do want to do though is I want to explain what I'm actually doing. So when you come into our RTMS piece, and it's not the software issue, it's something to do with my relay. So in this picture here.
Hey, David, I would like to step in here. Can you check your output contact? Is this the programmed for the right contact?
It's not. It's not. It's not going to program because the webinar is on. Okay. All right. So since it's hard to run multiple things at one time, I think it's what's killing me is my communication between my PC and the relay is not talking. It's not making good connectivity there. I am driving the test set, just so everybody knows. I'm injecting the current amounts like we talked earlier on how we were actually doing the inverse curve. And when you come into this screen is our tolerance that you guys are seeing. We have the 50P1T is the element here. I have selected multiple phases, whether I'm doing A, B, and C, A to B, B to C, C to A, or a three-phase test. Also, I have picked up this value for my pickup value out of my settings. I've pulled in the time dial, and the time dial setting actually comes from the settings as well. I've selected the SEL, right, which is the relay that I showed you before, and then also the U3 curve, which is part of the settings in my settings screen. It's also in the slide that I showed previously as well. And so when you select into this timing screen, what we're doing is I selected these values 2, 3, and 5 times, right? So if I want to change these values, I can. Some people don't use the same ones, so they'll do 2, 4, and 6. That's fine. You can change those, or you can also change the test current as well. So if you don't know what the multiple is, and you just know that my test current is going to be 10 amps on one, and it's going to be 15 amps on the next one, you can also apply those by current as well, and the software will accommodate itself no matter which option that you choose to go with. And why does it do that? Because it, like when I was talking about earlier about the inverse curve, you can either go off of time, we can go off of current, and we still get to the same point. So if I hit run and select here, as Mohit came on and addressed, I have a communication issue going from my PC to my relay. I'm not able to perform the element masking. So I would mask the 51P1T to out 107 of the relay using the accelerator software. This software just will do this as well, also do the masking, but I'm also lost some type of connection, or I would say some type, it's my USB going to the relay. So in the explanation, we will do this as a simulate option here, so you can see the finished, at least the time current curve before I run. I've already ran out of time. I'll at least show you at least one though. So as you can see, the current values that we chose are coming up, and then also we're going to plot these on a graph. I'm not a good relay, so it's going to kind of catches you off guard. It's almost like playing a little video game here. Oh man, it's running all the, okay. So we're running all, I get multiple shots at this. We're doing a little over 2 times the multiple because, why? Because I chose 15 amps over here, which is 3.16 multiple. And you kind of see the idea, right? The idea is that we're actually providing a current multiple and we're waiting for the relay to operate on a specified time from the time current curve or U3 curve that we have selected in this relay. Okay, so I will go ahead and abort this for time's sake. I want to apologize. It didn't. Everything didn't come up as I would like for it to have. But the general idea, we're still, whether I simulated these devices or actually ran them, it's just running current into the relay. The relay is making a decision: am I over the threshold? And then we're providing a time, and we are capturing these times. And these times are important to actually go into our report as well. Okay. I would like to turn this back over to Mr. Mike. And
all right, thank you. If you could, beautiful. All right, so at this time, the presentation portion has officially concluded. We're going to have a few minutes to answer as many of your questions as possible. If you have questions, please submit them now into the Q&A box on the bottom of your screen. As a reminder, we do have one more segment after this Q&A session, so please stay tuned. So our first question is going to be directed to Sugosh. Instantaneous is never really instantaneous. Can we calculate the magnitude of this instantaneous time?
Yes, it is possible to determine this instantaneous time. The easiest way to do this is by running a timing test on the instantaneous function. So you could have 2 stages of test set, wherein you can create a pre-fault state and then switch on to a fault state wherein it actually injects the instantaneous value, and then the relay trips for the instantaneous time.
All right, beautiful. While I have you, Sugosh, David, if you would mind going to slide 14, I believe they were referring to that one when they asked this. How do I choose between these curves? What does it depend on?
I'll wait for David to go to slide 14. So yeah, you would need to perform the short circuit and coordination studies, and then you could use these curves based on your studies in combination with the thermal capacity of your lines being protected.
Okie doke. So Mohit, next question is going to be for you. What is the difference between TAP and PSM?
Okay, so TAP and PSM both are used frequently for electromechanical relays and sometimes for solid state relays. I have not seen them being used for the microprocessor relays. The difference is TAP, the value of TAP is actually nothing but your pickup value for the overcurrent element or over voltage or what kind of relay you're using. Whereas the PSM, which is the abbreviation for plug setting multiplier, is actually the ratio of the fault current to the pickup current of the relay. So there is a minor difference between the TAP and the PSM. So I hope I answered the question.
I believe so. Next question is going to be from Marius. Can you test a breaker trip unit over current elements utilizing the relay test equipment? Marius, do I have you over there? Looks like we might have lost Marius in the system.
I can answer that question.
Oh, thank you.
Yeah. So yes, we can absolutely test breaker trip unit with the relay test set. We have a feature of recording time on our home screen, so anybody can use a pre-fault to fault home screen, provide nominal values on pre-fault, and then pick up values for the breaker trip on the fault state. And all they need is a way to connect to the binary input of the test set. So because the binary input on smart units is a banana jack type input, so the user would need somehow to convert the trip unit contact, connect with a wire or something, and then make a connector to the banana jack and connect to the binary input. That way they can record the time. We have the ability of recording the time in seconds, milliseconds, and cycles. So anybody can have a neat, decent report if they want to see the value in second cycles or milliseconds.
All right, thank you. Back to Mohit still. How do you perform phase and ground element testing at the same time?
Okay, yeah, that's a really good question. A lot of times I've seen people telling me not to change the output contact, not to change the output contact. That's a good way of testing, not manipulating with the output contact and keeping basically just testing what it is on there. So for example, if a 51P and a 51G element are both sitting on the same output contact, usually the 51P element would have a higher setting because it's related with the phase side of the system, whereas the 51G would have like a lower setting. I would like to give an example so that everybody can understand what I'm talking about here. Let's say the 51P is having a pickup of 6 amps and your 51G is 3 amps. So the trick is you start injecting current and you are injecting, and the moment you reach 3 amps, your 51G will pick up. So there is no way to test 51P, right? That's the question everybody is asking. But there is a way actually you can do that with our software. There is a feature that we have called as phase compensation on our screens. What it does is it provides the value of phase. Let's say you're testing phase A's. It would provide current value on phase B and phase C such that the zero sequence current turns out to be 0. So you can increase a phase value, but in the similar way, you can actually keep the zero sequence current to be 0. So your 51G would never pick up, but you can test your 51P. So that's how you do the testing using symmetrical component theory.
Thanks, Mohit. So our next question is going to be for Sughosh. With time coordination relays, upstream may take longer times to operate for faults near the relay. Is there a solution for this?
Yes. In this situation, what you can do is you can consider the distance relays, wherein what distance relays does is that it utilizes the voltage and the currents to calculate the actual impedance on the line. And no matter where on the line the fault is, how close to the relay it is, as long as it falls within that first zone of protection, the relay is going to trip. And coming back to the question of upstream taking longer times, the distance protection zone 1 especially will trip instantaneous, so we don't have to worry about the longer times.
Beautiful, thank you. So Mohit, I have a question for you. Can overcurrent elements misoperate for faults not on the protected line?
Yeah, absolutely, especially on radial feeders, because overcurrent elements, I'm assuming the question was asked related with the non-directional overcurrent elements. So non-directional overcurrent elements, no matter where the direction of the fault is, if the value is higher than the pickup, the relay will trip. So in that case, the fault can be not on the line, but on the backside, and then it can trip it. So that's why we provide solutions such as directional overcurrent relays. So the answer is yes, it can misoperate.
All right. So Sughosh, does the RTMS software allow for different frequencies, such as an aircraft, which would need 400 hertz?
Absolutely. So on the RTMS software, we have the option to obviously change these frequencies independently for different channels of currents and voltages. Another nicer feature on this software is that you can generate frequencies of different levels on the same channels. So one channel can generate of up to 4 waveforms of different frequencies. I hope I answered the question.
All right. David, do we have you over there?
Yes, sir.
All right. Are you ready for your next question?
I believe. Bring it.
Okay. Please explain, how do you make the test files? I'm specifically talking about all inserted values.
Okay. So what we do is when you're creating the test files, we actually are, once you run the test, so you'll set up your ramp or your timing function. Once you create that timing function or the ramp that you want to perform, even if it's from the home screen, you can do a pre-fault fault scenario. And then once you get that ran, it actually will give you an option at the top by the report. It says add to report. If you're in the timing screen or one of our predefined, like a transformer differential screens or a state sequencer, then those automatically populate that test into a test file. And as you were looking, I was going into the T with the lightning bolt, would actually give me my different tests and allow me to group those tests how I see fit. So if I wanted to utilize the settings that I pulled out of the relay into the test, then all I have to do is right click those settings and then apply them into a small script function that's built inside every test. So what it would probably be a better idea is to kind of get the information, your information, contact information. It gives us an opportunity to kind of step through it a little bit and walk through it. So if you wouldn't mind, whoever asked that question in particular, be sure to leave us your email. And if not, when you do the survey, I believe, Mike, you can do write email or some comment on there that would like to see the RTMS templates, then please put that on there. And then that way we can reach out to you and we can do a screen share. And then that way I can kind of walk you through it a little bit.
All right. So our next question is going to be for Mohit. So in regards to the rules for coordination, what does the same operating characteristics of relay mean?
I'm assuming they were referring to, David was referring to the curve type in the relay. So you can have the same curve type, but if you change the time dial, you can coordinate a downstream and an upstream relay. So having a U3 curve for SEL relays, and you can have like a time dial 2 for one relay, whereas the time dial 3 for the other relay. So you can have like some kind of time compensation there. Hey, Mike, before we proceed, I would like to point out another answer of mine, which I told about the timing unit on the breakers. I see that Mariano is having an objection in there. He is referring to using a primary current injection test set, which is absolutely correct. Definitely, primary injection test sets can be used to inject the values of high currents on the primary breakers. And then you can measure the trip time using the primary injection test sets. I was actually referring there if you have a trip unit sitting on the table or on the bench. And then if you just want to test a trip unit, because I've seen multiple customers doing that, they don't do it when the trip unit is connected on the breaker. They just do it, keeping it on the bench. So you can still provide secondary injection values to that and then be able to test it.
Thank you for the clarification. David, I think this will probably be our last question we have time for. How do you perform a wiring checker test?
What we're referring to in here, a wiring check, I'm assuming I'll go with trying to perform a check from the test set, verifying that the correct currents and voltages are actually wired to the relay properly. Whether they're operated to the back of the relay where we're connected to it on the bench, or we're also doing test switch if it's plugging into a panel using a test switch and going up. We do have a meter function inside RTMS as well. And then it's actually allows us to put in a current, voltage, and some angle, and then each individual phase, and then it'll go through and calculate whether what the applied values compared to the measured values are correct or not. And that kind of gives us a quick wiring check. I hope that's what I'm answering, or if they're answering that correctly. If not, again, leave us some information. We have email, we have survey. That way we can better answer the question as well. But hopefully that kind of gave you an overall.
Thank you.
Answer.
Yeah, all right, so it looks like that's all the time we have for this Q&A segment. We're going to jump into a quick 5-minute intermission, and we'll return for the second presentation of our seminar, so please stay tuned. Don't drop off. We'll be right back. It looks like our 5-minute break has concluded. Mike, if you are ready, I will relinquish control over to you to share your screen.
Okay, it looks like I'm ready to go.
All right, excellent. Give me one moment. So, thank you everyone for staying with us. We will now begin our second presentation. Our second presenter today is Mike Ditmore, Relay Application Specialist. As before, to assist, we have 3 panelists joining us. We have Mohit Sharma, Applications Engineer, Marius Pitzer, Product Manager, and Sugosh Cooper, Applications Engineer. Okay, let's go ahead and get started. Thanks for joining us, Mike.
Okay, well, thank you everyone for coming back and joining us for the second half of this virtual best practice seminar. This afternoon, I'll be talking about reclose relay schemes and reclose relay testing. Okay, for a quick agenda, we'll start off by talking about definitions as they apply to reclosing. Fault types, again, as they apply to reclosing. And we'll talk about 2 different reclosing schemes, faults, fuse saving and fuse blowing. And then we'll move right on into Recloser control testing. We'll just look at it briefly, and then we'll actually test a reclose relay with an SMRT46 and RTMS software. Okay. The standards that apply to this presentation is IEEE C37.2, function numbers and acronyms, and C37104 is the guide for automatic reclosing of circuit breakers, both distribution and transmission. Pardon me, just one moment. Okay, and I'm back. Sorry about that. Okay. Now, while we're discussing timing, traditionally, reclosing has been expressed in cycles, at least in North America. Most relays are transitioning now to discuss seconds and milliseconds. I'm testing a Schweitzer 551 today, and it uses cycles. So just for consistency, most of my discussion will be based on cycles, and specifically it will be based on 60 Hertz. Okay, so what is dead time as it refers to reclosing? It's quite simply the time period between a breaker trip and a reclose. It's the total time that the cable is de-energized during that interval. Okay. High-speed reclosing. It's pretty obvious what that is. However, it does have to include a little bit of a delay to allow for the ionized gases to dissipate. And we'll be talking more about that a little bit later. A high-speed trip is a trip with no intentional display. And as I was going through some of the questions from the first section, I noticed that question was asked, and you'll actually see an example of where we determine what that delay is. Lockout. This is not the lockout handle in a control house. This is not an 86 device. Lockout in this case is referring to the lockout state of your reclose relay. This simply means that the reclose relay is inhibited from issuing any further reclose attempts. And the word shot is a reclose attempt from the reclose relay. ANSI numbers that we'll be using relevant to this presentation is 50 is an instantaneous overcurrent relay, 51 is a time overcurrent relay, and 79 is a reclosing relay. Okay. So why do we actually want to reclose? Well, it's quite simple actually. Most faults, 80 to 95%, are not permanent. They are non-persistent. Some of these will be transient faults. Some of them will be temporary faults. So let's look at what the difference in those are. Transient faults, events such as lightning strikes, conductors slapping together, things like this. Overhead lines are susceptible to these things on a daily basis. Most transmission lines actually have a static shield wire that goes on top of the conductors that helps reduce the lightning strikes, but they still see a fair amount of it. In this situation, generally speaking, and there are plenty of exceptions, damage is somewhat minimal and sometimes even non-existent. A temporary fault is something a little bit longer to clear. Animal contact and vegetation contact are clear examples. However, either of these can become permanent depending on the situation. If an animal doesn't get blown clear, unfortunately that does happen. If it's still in contact with the power line, it may become a permanent fault. In a storm, maybe you have trees blowing and slapping up against a power line. Trees maybe need to be trimmed. Sometimes these need a little bit of time to blow back and recover. And then other times the storm is whipping and gusting and the limb continues to blow over and blow over and blow over, and it accumulates to what appears to be a permanent fault. Many times these things just need a little extra time to clear. So a second and maybe a third reclose attempt will give it time to do that. Permanent faults are fairly obvious, I think. Downed power lines, equipment failure. Equipment failure would include things like failed cable terminators, cable junctions where they go underground, things of this nature. Distribution transformers generally are going to have fuses on them, so damage to their windings or anything that happens inside that pad mount generally is not going to be a permanent fault. Okay, so once again then, why do we want to reclose? Well, shorter outage time improves customer satisfaction. Anytime the electricity is offline, it is not being sold. So we want to maximize revenues and we want to maximize satisfaction. And in the process, especially when we add this together with a successful reclosing scheme, we reduce the manpower required to go out and do restoration. So we'll talk about just a few of the key considerations, and this is by far not a complete list of key considerations, just a few to get you thinking in the right direction. But what is the probability of a successful reclose? Well, overhead power lines clearly have a greater success rate than underground power lines. Why is this? We have transient faults, more temporary faults. Many of these faults, like it said earlier, 80 to 95% are not going to be permanent. During this time, they sustain little damage and sometimes no damage whatsoever. And then we have a reduced probability of success. The more underground we have on it, the less chance we have of reclosing. That said, this is still a good situation because underground is subjected to a mere fraction of the faults of overhead. If you have a situation where an entire feeder is underground, there's a good chance that feeder would be operated with no reclosing at all. Underground faults are usually going to sustain greater damage. You may have stress cones fail, you may have other cable terminators fail, that type of thing. Okay. So how do you figure out what your reclose times are? Well, unfortunately, the current release of the standard C37104 provides very little guidance. We do have good information that this is under review again, and in a reasonable time period, we'll expect a new release, and we are expecting to have good guidance for reclose times included in the near future. Right now, however, it talks about ionized gas dissipation, and it needs 20 cycles of total dead time in order to let ionized gas dissipate. The other thing it talks about is just a very broad-based dead time interval suggestion. First trip, it says is 0 to 5 seconds. Second trip, 10 to 20 seconds. Third trip, 10 to 30 seconds. And any additional trips are not even addressed. One further comment about the 20 cycles dead time here. If you really were concerned and needed the most rapid reclose you could get to, this does include breaker closing time. So if you have a good understanding of your breaker mechanics, or if you have that timed, you can include that. But realistically, I don't think 3, 4, maybe 6 cycles at the most would make that much difference in most applications. And you would run the risk, if you don't quite get the gas dissipated, that you would run the risk of a restrike. So now we're going to talk about the 2 reclosing schemes. One of them is fuse saving scheme, and the other is the fuse blowing scheme. I want to point out right to begin with that the difference in these 2 schemes is primarily the way in which the first instantaneous trip is handled. To some extent, it also covers the first reclose, but it's really the first instantaneous trip that matters. Okay. So let's go into fuse saving schemes. Okay. An overview of the fuse saving scheme is we're going to use a low set 50 overcurrent relay. Low set meaning about 120 to 150% of maximum expected load at the substation breaker. Now this maximum expected load needs to include any kind of emergency or contingency considerations. Almost every distribution feeder out here has the ability to be tied to an adjacent feeder, either for maintenance or if you have a problem and they need to pick up load and spread it around. So you have to look at the total maximum expected load under any circumstances and then set it a little higher, about 120 to 150%. Now, high-speed tripping is indeed not high-speed tripping. Well, it's high-speed, but it's not instantaneous. Okay. The first thing we have is relay propagation time. It varies depending on the relay, depends on the type of output contact, but generally this is the time period required for the relay to sense the fault, make a decision, and close its contact. It's going to run between 1/2 and 1.5 cycles depending on the relay. The newer relays hitting the market now are getting a little bit faster than this. They use static outputs and they can switch on. I've actually seen one down now to 0.2 cycles. I don't know how common that's becoming, but it is something that's breaking into the market. Okay. Another delay that we cannot do anything about is breaker time, the mechanics of getting the breaker open. You have a little bit of time associated with the trip coil actuation, a little bit with the breaker moving. You have the contact parting and the arc time. All of that accumulates together and you get somewhere in the neighborhood of 3 to 5 cycles. It's hard to nail down any closer than that because every breaker is different and relays are different. Okay. This is about the time it takes to get the breaker open and extinguish the fault. This is an actual recording of a phase to ground instantaneous trip using a typical vacuum breaker. The measured time from when the arc was established until the arc is extinguished is about 3.5 cycles. So let's look a little bit deeper on this. If you look in the pre-fault section, you can see a little bit of pre-fault current. It is hard to see because this is auto scales to allow for fault current. It's definitely, you can see pre-fault. You can also see good, healthy free phase voltage down here. And then you have the fault strike. voltage decays immediately. That's how you can usually tell the exact moment that the strike occurred. Current rises quickly as well. Throughout the fault, you can see voltage is maybe 30–40% of nominal on the faulted phase. The other two phases are a little bit affected, but they're almost normal. Okay. Then finally, the breaker starts to come open, the arc starts to go out, and right here you can see where it's extinguishing. And then in the post-fault, you can see truly that there is zero current, and you can see this zero current compares to very slight load current. You can also see healthy voltage has been restored. So we had about 3.5 cycles of unhealthy voltage and high fault current. Okay, so no matter how fast we trip, and again, we are talking about fuse saving schemes, we actually tripped, we interrupted the fault, and the fuse did not blow. But in spite of that, the fuse is going to sustain some damage. You have a little bit of a fuse melting going on, and then it recools, resolidifies. Most fuses actually have a spring inside that holds tension on the link. The spring is used to accelerate the movement when the link parts, so that it helps to interrupt the fault. That tension, a little bit of accumulated melt, if it gets hit with 3–4 faults over time, a little bit of micro vibrations with the wind going on, and you can have a fuse just give up and drop out at an unpredicted time. It might be associated with another fault on its branch, but it might not be. It's very hard to say. It could be the summer sun is the final factor. Now we're going to talk about fuse blowing schemes, but before we do, let's just take a moment and recap fuse saving. Very briefly, fuse saving permits whole feeder momentary outages. The intent is to prevent longer outages to the entire faulted circuit. Fuses will accumulate a little bit of damage and at some point are subject to unpredicted failures. Now we'll go into fuse blowing scheme. Fuse blowing scheme intends to give this fuse time to go ahead and blow. Time overcurrent coordinates with downline reclosers so that everything is protected. The intent here is to interrupt the fewest number of customers rather than a momentary outage that trips the whole feeder. A fuse blowing scheme says we're going to preserve all these customers, and these customers, just this small number, will be outaged for a longer period of time. One of the reasons that this has become more popular is that electronics has become more and more sensitive, and more customers are unhappy about momentary outages. A lot of manufacturing processes, even just a momentary blink is enough to reset their logic controllers, and that interrupts their manufacturing process. Okay. So in this case, how do you determine the minimum trip setting for the 50 element? Well, you look at the maximum fault current at the recloser itself, at the first downline device. You don't want to go past this. And so most would set the 50 element to trip for a fault current about 80 to 90% of the value at the recloser. If you try and get it too close, understanding that cables are different, the return through earth is different, there's a lot of variables. You can't set these things too close. If you try and set it right up to the recloser and then you have a fault maybe on the first span past the recloser, there's a good chance this breaker would overtrip for it. So you want to stop about 80 to 90% of the calculated fault current based on your fault study right here. Okay. Now, 50 element is an instantaneous element, and we showed earlier that we can trip the breaker fast enough to save this fuse. Well, that's not what we want to do now. So we have to put a definite time delay into the 50 function to prevent it from tripping too fast, to give us just enough time to let the fuse part. Through experience, it's been learned that 2 to 5 cycles is plenty of time to get the fuse open. So now what has that done to our total clearing time? Well, our relay propagation time hasn't changed. Our breaker time hasn't changed, all the time associated with the trip coil, the mechanism, the contacts, and the arc, but we have added a definite time delay. So now we're up to about 5 to 10 cycles total fault clearing time when you have a fuse blowing scheme. Now that's assuming that you're tripping on the main line and not on a branch circuit. So before we move into multi-shot reclosing, let's just take a moment and we'll recap and compare a little bit between fuse saving and fuse blowing. Fuse saving scheme allows momentary outages on the entire feeder, while fuse blowing scheme accept longer term outages for the smallest number of customers. Understanding that in this case, someone always must respond and reset that fuse. So it is a significant time outage. Fuse saving scheme results in damaged fuses, which may drop out at unpredictable times. Fuse blowing schemes, like I just said, requires a worker to always respond and put in a new fuse, reset the recloser, whatever is required. So now with that understood, we'll move on into reclosing, multi-shot reclosing, excuse me. Okay. Many feeders, I would say most feeders in the world today, have multiple shot reclosing. 2 and 3 shot reclosings are very common. 4 shot reclosing, maybe a little bit less common. Okay. Already stated a couple of times, the standard does not give us a lot of good guidance regarding reclosed intervals. So how do we come up with these numbers then? How is it possible to figure it out? Well, the first one is understood. The fastest that you can reclose on any fault is your 20 cycles required for gas dissipation. The real answer just comes through experience. Utilities have developed their own reclose delay policies and procedures based on experience and based on experience with their specific customers and considerations. I know that some companies, larger companies, don't have a set process because it depends a little bit on where they are. They'll treat rural areas differently than they'll treat metropolitan areas. And when you think about it, that makes good common sense. But again, it comes down to experience. As I previously stated, the standard is being worked on, and we will soon have good guidance for what these numbers should be. So now let's look just a little bit about the overcurrent relaying. Now, David Beard just earlier today talked a good bit about overcurrent relaying, so I'm not going to go over this too deep. I'm going to focus on how it impacts reclosing. Just a little bit about the time curve here, and this is actually the time curve of the relay that I'll be testing here shortly, and this dot is a predicted trip time for the fault current that I'll be applying. So in this case, it's set up to give me time and cycles, and on this axis we have multiples of pickup. Notice that it's a log graph. Pickup, by definition, is the tap at which the timing begins. So if we have a relay set on 10 amps, this 1 would be 1 times pickup, or 10 amps. With this being 10, you can see that this becomes 2, 3, 4. So if we have a pickup set on 10, this becomes 2 times 10 for 20 amps, 3 times 10 for 30 amps, etc. As far as your predicted time goes, if this is 100, this is 800, that becomes 200, 300, a little over 300 cycles to trip. Okay. This is based on a Schweitzer 551 U3 very inverse time curve. But we're also talking about reclose coordination. So reclosers have similar curves, but they're shaped differently. And this is just a random curve that I selected. Didn't have any rhyme or reason to it. Reclose curves come in many different characteristics. Some curves come out here and do odd shapes like this. A good number of them will come in here, drop steeply, and then flatten back out this way. But you have to be able to overlay these onto a common graph, do a study, and be sure that this curve is functioning behind this curve. And I'll explain that in a moment. Okay. So what we're talking about now, if we have a fault past the recloser, we're coordinating the time over current function. And in this case, the closest device to the fault has primary tripping responsibility. This recloser should be operating a little bit faster, not a lot, a little bit faster than the relay at the substation. Now, throughout the history, induction disk relays have been around a lot longer than electronic and microprocessor relays. And I know there are thousands of these still in place today. So when you start looking at how these coordinating factors apply with reclosing, you have to look at the reset time of an induction disk relay if that's what you have installed. If you don't allow enough time for the induction disk to reset before you reclose the recloser or reclose the breaker, if you don't allow enough time for that disk to reset, the disk will tend to ratchet forward, meaning that if the fault restrikes, the disk begins to turn forward again, but it did not start from zero. It now has a shorter time before its actual trip time will expire. So on the first reclose, you might be okay. On a second reclose, there's a good chance you're going to miscoordinate. And if this is where the induction disk relay is, the fault is here, this guy could possibly beat this recloser out, and now you're not really coordinating properly anymore. Okay. When you have microprocessor and most electronic relays, generally they're going to have an immediate reset option. Gives you a lot more flexibility in your reclose scheme. Okay. So this is the equations for calculating trip time and reset time in the relay that we'll be testing today. And these are very applicable. It's the same curves that will be used in a coordination study to determine where you are. So you have predicted trip time involves your time dial, and I believe David talked about that earlier, but mechanical relays actually have a disk that spins around, and the only way they adjust how long it takes them to trip is by turning the disk so it has further to travel. And it's actually done by turning a dial, and that dial is graduated 1 through 10. So it was time dial. Then the equation also takes into account the square of the multiple of pickup currents put onto the relay. So what we'll be testing today has a time dial of 4. And I'm just going to be putting on a 2 times multiplier, and that comes out to 333 cycles for predicted trip time, and we'll actually see that take place. The reset curve for that same relay takes the same things into account. If you have disk emulation turned on, this is how you would calculate how far back the reset has traveled. It takes into account time dial, it takes into account multiplier, but because I'm actually putting 0 current on it, the equation simplifies and it just becomes time dial times the factor of 3.88. And this 3.88 is provided by the manufacturer. These equations come directly out of the user guide for the book, for the relay. Okay, and so that actually comes down to almost 16 seconds to reset. The reset time is very slow, and if you've ever seen an induction disk relay work, you'll understand that you can reach up and use your finger or the eraser on a pencil and reset it faster than you can wait on it to do it yourself. Okay. Now this is an example of a miscoordination, which obviously I set it up on purpose, but I recorded this for the sake of this presentation. And here you can see the first trip was high speed. It took 1.32 cycles. This is a good benchmark for your relay propagation time. It does not include breaker mechanism time. I didn't have a circuit breaker connected, but this is a good estimation for the relay propagation time of the Schweitzer 551. And this is a reasonably stable number on most Schweitzer relays with the same type of output contact. They're going to fall in the same ballpark. Okay. Trip time 2. So I simulated a trip, I simulated a reclose and a restrike. Actually measured 334 cycles. Okay, so we looked just a moment ago and we said it was going to be 333. And now we're measuring a little over 334. When you add the propagation time, that's pretty close. And then we get to fault number 3. And oh my, we had a 66 cycle fault time. So why did it come out so short? Because I had disk emulation turned on. That's what I was demonstrating. So the time period, the reclose time period between fault 2 and fault 3 was only 180 cycles, I believe. Let's see, second reclose. That's right, 180 cycles. So in 180 cycles, it only reset partially and we tripped very fast. Okay. So what does all this mean? If you have a high-speed trip, then your first reclose can also be high speed, keeping in mind your 20 cycles here. If you have a time delayed trip, any reclose needs to take into account the reset characteristic of that element. Modern relays, if you have disk emulation turned off, much more flexible. If you have mechanical relays, you have to really take this into account. It causes you to extend your reclose time significantly. So now we're going to walk through kind of a step-by-step of what happens during a reclose sequence. Okay, so we start off, the breaker's closed, load's being carried, everybody's happy, conditions are normal. A fault occurs, the 50 function asserts, and a trip signal is sent. Breaker comes open. The reclosing function begins timing towards shot 1. Shot 1 expires, sends a close signal, breaker closes. Fault restrikes again. Okay. Most of the time, 50 functions are disabled after the first reclose. Actually, they're disabled before the first reclose. So now a 51 function takes over. This is intended to give that fuse time to blow this time. We don't want to lock out the whole feeder. We really want to just let that fuse blow this time. So it finally timed out. It gave the trip signal, the breaker's open, and now the recloser is timing toward shot 2. Shot 2 expires, use a close command, and the fault restrikes again. Okay. Once again, 51 takes over. Until the reclose feature of this relay resets to 0, it's going to keep the 50 function blocked. Okay. 50 function times out, trip signal is sent, breaker opens. So now we're timing towards shot 3, and this will be a little bit longer time. This may be up to 3 minutes, 5 minutes in some cases. It finally times out, breaker's closed again, restrikes, 51 function asserts. This time, however, it reaches lockout. As soon as the 51 function asserts, a trip signal is sent, the breaker comes open, and the whole thing is over. Pretty straightforward. Okay, so in conclusion, the reclosing of the distribution breakers is effective for maintaining customer satisfaction. Reclosing schemes vary pretty widely, but they generally will fall into the 2 categories of fuse saving or fuse blowing. Fuse saving is effective where response times are great. Maybe low density is not quite as much, the more rural areas. Fuse blowing seems to be more effective where you have more sensitive electronics and where response times are much lower. So this would be your metropolitan areas. coordinated multi-shot reclosing is effective with both schemes. Okay, so now we're going to jump into electronic recloser testing. And okay, so in general, reclosers, with regard to reclosing, are very similar to a breaker. Both a recloser on a pole or in a switchgear and a breaker in a substation provide multi-layers of high-speed tripping, time-delayed tripping, high-speed reclosing, delayed reclosing. They function very similar with regard to their basic trip and reclose functions. So how do you test them? Well, we actually provide an interface. This is not high-tech electronics. There's no power supply. You don't plug it in. There's really no place to even connect a computer to it. You don't need it. This provides connectivity to connect to the recloser controller and to the recloser on the pole simultaneously. So it provides connections so we can connect our relay test set to inject voltages and currents. Currents you can connect here, voltages. If you notice, we have two sets of voltages. So we support the ability to inject line side and load side voltage. And if you know reclosers, you'll understand that can be very important. Okay. It also gives us the ability, the connections, to be able to record all trip and close commands that are passing between the recloser and the controller. And it allows us to monitor the state of the recloser itself. Okay, so how does this work? You have the cable coming down the pole that would typically connect to the recloser controller. You take it loose from the controller and you plug it onto the back side of the instrument, and then you take a shorter temporary cable and connect it from the top of the instrument to the controller. So this connection device is now in series with the controller to the recloser. Now, assuming this cable also includes your sensing devices, that's your voltage and current devices, we're actually not passing these through. They're stubbed out at this point and they're not in use. And they're isolated because we're now injecting current and voltage back into the controller. We want the controller to look at what we're telling it's going on, not what's really going on. Now, this does assume that you're in bypass mode or otherwise de-energized. You would never do this with the recloser in service. Okay. As far as the actual test sequence goes, there's no substantial difference from the relay test set perspective. There's no substantial difference in testing the recloser function of a recloser and the recloser function of a relay. They're very, very similar. The big issue is how do you get your connections accounted for? Okay. So now a brief look at other products that we have available. We have our single phase, all our multi-phase. We have our manually controlled three-phase test set. It's a great entry-level product. It's also a great tool if you're commissioning stations. It's very easy to use. David, I think, pointed out that we have several display versions. This would be an example of what you might see on the display version. If you don't have a display version test set, whichever one you might have, you have the option of using a handheld if you wish to do it. Obviously, you can also just use your computer. And then we have our recloser test set. Okay. So now we're going to move into the product demonstration process. We're going to be testing a Schweitzer 551. All faults will be single phase to ground. SLRT 46 will simulate breaker actions, tripping and closing. And in the relay itself, I have severely simplified the logic, and you'll see a little bit of what that is. Okay. The settings we'll be testing are very simple. I've used very low settings, no point in straining the relay. We're going to be testing the 50 ground number 1 pickup point is set to 3 amps. The 51 time overcurrent ground number 1 pickup point is just set to 2 amps. I'm testing a U3 curve, and I'm testing a time dial 4. Unlike the sample that I showed you earlier, dissimulation is now turned off so we can have higher speed reclosing. And the trip equation is, I've really taken it down to the very basics. We have the logic for 50G1, that's your instantaneous ground. As long as the relay is reset and the shot counter equals 0, we have high speed tripping, or we always have time over current tripping, 51 ground time over current tripping. Okay, and we have our open intervals. Reclose intervals are set to 60, 180, and 360 cycles. There's 2 different resets in a relay like this. One is reset from reclose cycle, that's 600 cycles, and reset from lockout is 300 cycles. These are actually factory default settings. I saw no need to change those. We actually will be testing all 5 of these characteristics, and while we're at it, we may as well capture 3 trip times as well. Okay, test connections. Single phase to ground, I'm really needing 1 current channel. Very simple. The relay is plugged into the AC. Almost all relays being manufactured today have a universal power supply with a wide range of DC and AC available. You just connect what you have and they come on. Okay, I'm using the battery simulator to wet a contact, and I'm going to take that wetted contact along with negative from the battery, and I'm simulating a 52A contact right here. Then the relay outputs, I have trip, close, and reset. 79 reset is attached to output 1, output 2, and output 3. And these outputs come over and connect to relay test set input 1, input 2, and input 3, all respective. 1 to 1, 2 to 2, 3 to 3. And with that, I'm going to jump over and begin testing. Let's see. Okay. Now, what you saw David do earlier today is use a test template. I actually didn't do that. This is a very basic test, so I just input everything manually. So I'm going to select new test. I'm going to go into sequencing. Okay, now I've already created the sequence, and I'll go over what we do here just a little bit. The sequencer starts off, I have 14 maximum states, but that can go up to 99 states. I don't know what you would be testing for the 99 states, but it can definitely do it. Each state is completely configured differently. So as you toggle through your states, you can have different values, different voltages, different currents, everything can be totally different. Okay. As far as your input contacts go, I've actually renamed the inputs so that I have a trip input and I know which one that is. I can configure it to be contact or continuity or voltage. In either case, it can be applied or removed. Okay. Same thing's true with your output contacts. I have this renamed to remind me that it's a 52A simulation. Okay. I can tell it when to open and closed. You'll see that some states it's open, other states it's closed. Okay. With every state that I go to, I have to tell it, what are we waiting to do? Well, the first state that I'm going to do, when I first turn on the test set, I'm going to be turning on the battery simulator, closing this contact, and the relay will begin timing toward reset. So I want to tell it to wait on something to happen. Wait on anything to happen. I could also tell it to wait on all to happen. So if I needed 2 or 3 contacts to close and all come true, then I can tell it to wait all. But I just need wait any. So I can do that for each state. Come to the next state. Well, first of all, on the first state, I'm waiting for the reset of the relay to occur. I'll capture that time, then transition to the next state. The breaker is still closed, but now I'm applying fault current. And now I'm waiting for the trip to occur. When that occurs, I transition to the next state. I'm now waiting for the reclose from the relay. I've opened the contact and I've turned off current. And we just do that repetitively, and we look for different items up here depending on what the state is needing. Okay, so we'll screw the timer setup just a little bit. Okay. I've named everything that we need to know. The first thing we'll be timing is reset from lockout. We're going to do one trip and let it reclose, and then we're going to pause and wait for the reset from cycle to occur. And then we'll be getting a trip and a reclose, a trip and a reclose, a trip and a reclose. The desired time I just put in parentheses right here just for my visual reminder. Okay, for each of these timer names and timer configurations, notice that I put in minimum and maximum. After we run the test, the actual value will show up here. But for each one of these, we have to tell it, what do you do? We have to tell it, when do you want to start? We found that it's best to start on a state. So as you enter the state that has that function needed, you just select what state do you want to start on. Stop condition most of the time is a post or a timer input. So in this case, post 1 is the same thing as input 1 right here. Post 3 is input 3 here, reset. So you click on it and you tell it which one do you need. You can also configure it if you need to. Okay, so you do that for each timer that you're interested in. Okay, you can also get kind of a time graph, a little sanity check to be sure that you're doing what you think you're doing. You can see here where I do the first fault, I'll let the breaker reclose once, and then we have a wait while we're waiting on the reset time, and so on. Okay. Okay. So with all that, what I'm going to do now, and I've already pre-checked the relay should be set up and ready to go. I'm going to turn on the battery simulator, and I'm going to press the play button, and then I'm just going to sit back and you'll see everything changing on screen. And what you'll be seeing is you'll see that a contact go open and closed a few times, and you'll be seeing these contacts go open and closed as the relay responds. I'm going to press play. See, I'm just injecting single phase current. Notice that the contact is still closed up here, waiting on a reset. We've got both resets. It paused briefly, and now we're moving into the trip sequence. There's trip 2. There's reclose. It's getting a nice long reclose time. Now we're going into trip 3. The test is almost over. Didn't take long. And here comes reclose 3. And now we hit lockout state. And then I need one more thing to just get this contact back open before we open everything up. And it's okay now to go ahead and turn off the battery simulator. And we can come in here and look to see what we've done. All right, so we expected 300 cycles reset from lockout. There's 301. Expected 600 for reset from cycle. We got 601. Instantaneous trip. We got a nice 1.38 cycles here, well within the time period that we would expect for relay propagation time. Then we have nice trip times of 333. Have them twice here, almost right on top of it. If you look at the desired 333 plus your relay propagation time, very nice. Okay, first reclose time. Again, you've got 60 cycles that we're looking for, and relay propagation time is pretty much the same thing. So you add whatever time it takes to close the contact to the 60, and we're sitting at 61 1/4. Same thing for 180 and 360. Everything lines up beautifully. Close that. And now what we really want to do is see what can we do to present this to a customer, to your boss, for your records. So we're going to add this report to the result to the report. And now we can come in here and look at this a little bit. So it's kind of a long test report, but there's a lot to report. Because we had 14 states that we have to go through. Every state, you have 3-phase current, 3-phase voltage, and representation for all of your binaries. Okay, so we come down here. Notice we're actually seeing some of our binary actions here. Okay. Notice down here, it's actually telling us that we open the 52A. Remember, I actually retitled that contact so we know what it is. Now here's the final test result that shows everything that we configured for the timer names, mins and maxes, actual values captured, and since all of the actual times fall within the min and max parameters, we get green checks for everything. Okay, let's go to page 2. Let's see, here we are. Well, it didn't go to page 2 for some reason. Now, the only thing that I'm not seeing is the chart that I showed you earlier. See, I may not have selected to have it go to, yeah, it says that it should be in the report. Let's try it one more time. Here we go. Okay. So here's our pass-fail answers. Here's our chart. Okay. And now we have a table that gives us everything that happened as far as when all of our binaries operated. It's a lot of detailed information. 4-page report for a quick, simple reclosing test, but sometimes you need this much granularity in your results. Okay. So with that, if I can find the right screen here. Okay, and with that, I'll turn this back over to Mr. Mike, and we'll take questions.
All right, thanks a lot, Mike. So we're officially wrapping up the presentation portion of this segment. We'll take a few minutes to answer as many of your questions as we can. If you do have any questions, please submit them now into the Q&A box on the bottom of your screen. For those of you that are leaving, when you close the webinar window, a brief survey should pop up on the screen, which will look different than our typical survey. We would greatly appreciate it if you would take a couple of minutes to provide your feedback so we can continue to improve upon future seminars. On the survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of the presentations, along with a link to the recording of the webinar, will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars on our website at us.megger.com/webinars. Be sure to join us tomorrow for the 2nd day of our protection testing best practices seminar. So let's jump into your questions. Our first one I'm going to send over to Mohit. Is it better to make CB trip before fuse due to the time spent replacing the fuse?
Okay. It could be. It all depends on the utility practices, as Mike was explaining in his presentation. Various utilities adopt the philosophy of fuse saving scheme, whereas some adopt fuse blowing scheme. So everybody in the fuse blowing scheme, basically you are all the fuses are gone, and then you have to send a manpower out in the field to replace them. So there is this manpower cost and the outage cost. Whereas in fuse saving scheme, it will be good because it will also increase the reliability in indices like psi-d and psi-phi, but it will decrease the momentary indexes, because the momentary faults there would be a lot of momentary issues that would happen. So it completely depends on what kind of system the customer has. But in like, if you want to just to summarize this, few saving schemes usually have like coordination limitations on the higher current levels. So you can take that in you can take that in account and then decide which one to choose.
All right. So Sugosh, next question's for you. Do you need a recloser system, or can the 79 element in a relay and breaker accomplish the same requirement?
Yes, it is possible. So in this setup, what happens is the breaker itself will be performing the tripping and reclosing action based on the currents that it is seeing in the circuit, and then the relay settings also for the 79 element. So the 79 logic in the relay will be monitoring the action of the breaker.
Okay. So the next question is going to be for Abel. In case of single phase reclosure, will that cause unbalance for the three-phase system, and is that okay?
Hi, that's a very interesting question, and it's at the heart of the, I would say, more encompassing question. Would you do single phase reclosing, or would you not do single phase reclosing and only three-phase reclosing? And the answer is, it depends. Yeah, in some systems, it makes sense to do only three-phase reclosing if the system is too highly loaded, for instance. If the system is too close to its nominal load, when you do single-phase reclosing, you are overloading the other two phases, and you could create problems with breakers upline, which could see an increase in the amount of ground current and things like that. And on the other hand, if the system that you have is mainly the load of that system is mainly made of three-phase loads, like, I don't know, induction motors and things like that, you do not want by any means to have single-phase reclosing. However, single-phase reclosing is attractive when you have, for example, residential loads and places where you have a lot of customers that do not use three-phase power. Or it could even be attractive in moments when the load of the system is not that high. And the beauty of this is that there are right now available solutions where you can do single phase reclosing at some times of the day and three-phase reclosing and on others. And you can, I would say, selectively activate the single phase and the three-phase reclosing of the Recloser system that you are using. So the answer to that question is, you need to verify with a proper load and fault study, and with the types of loads that you have connected and the service level agreement you have with those customers, whether it is a good solution for you or not.
Thank you. Hey, Mike, could you bring us to slide 33 for this question, which is going to be for Sugosh. What is the meaning of curve U3? We'll page on over to that real quick.
Sure.
There we go.
Yeah.
Beautiful.
So the U3, it stands for one of the type of curves. It's a time current curve that is based on the IEEE standard, and this option it's present as an option in the relay curve settings. So Mike used this curve in his slides for explaining his examples.
Thank you. Our next question is going to be for Abel. If we have an electromechanical relay as a backup and a microprocessor relay as a recloser, what recommendation do you have on coordination, lag time, etc.? Or sorry, time lag.
Hi, another interesting question, and the answer to this one is do a proper short circuit study, and the tool that you're using can tell you what is the proper coordination times that you have to use for both. Fortunately, today, microprocessor relays can be coordinated whether downstream or upstream with other microprocessor relays and with electromechanical relays. Now, electromechanical relays have a feature, which is that they trip in one curve and they return or drop out on another. And that is something that can make it a little bit challenge to coordinate. So it's better to use, and the ability that we have today, a computer program to do the coordination rather than relying on, I don't know, hard and fast rules of use this many cycles and things like that.
All right, thank you. Question from Mike. What is a fuse dropout?
What is a fuse dropout? In short, that's when a fuse maybe has been damaged. There's no good reason for it to blow at that particular in time, but because of previous accumulated damage, it just fails and opens up. I mean, it's kind of a simple situation.
All right. Abel, your next question is, what does the M value calculate? I assume still on slide 33.
Yeah, we are in the proper slide to answer that question. And the answer is M is the multiple of the pickup current that is being injected as fault current to calculate the amount of time that it will take for the curve to trip. If you see there, Mike is using multiple 2, which means that whatever the pickup was, we are injecting twice as much current to that relay or to the fault, and we're getting that, that time. That's the way we have to make the curve independent of the actual amount of current, and we make it dependent only on the pickup value that we choose.
Thank you. Mike, could you please explain more about ionized gas?
Ionized gas, that's a very good question. There's actually 4 states of being, but most people think there's 3, but there's actually a 4th state called plasma. When you strike an arc, the extreme heat and the power that goes through it actually has atomic changes that take place on particles. Those particles begin to turn into plasma, which is one way of saying ionized. Ionized and plasma are very similar. So these particles are now conductive. Until they dissipate, once you remove all that energy from them, until they dissipate, they remain being conductive. So if you reclose too quickly and this particle stream still exists where the arc was, then it'll restrike through the same particle stream. You have to give these particles times to basically blow apart or just dissipate naturally, so they're no longer in close proximity to each other. But it's actually passing through the state of plasma to get there.
All right. So Abel, next question's for you. Why is connecting the load and line side voltages to the Recloser test set important?
Well, that's a very smart question, because it's someone who knows that there are reclosers out there that are not dependent only on the amount of current, even though the recloser operation is mainly done because of the amount of current that we have in the system. A lot of reclosers out there use voltages from both the line and the load sides in order to do some sort of automation. In some cases, what you do is you sense voltage on one side, let's say on the load side, and sense voltage on the line in order to verify that there will be proper synchronization when you're doing the reclose, just in case that you have some sort of feedback from the other side. Or when you're doing automation, sometimes you have schemes that use the voltages and currents, and not only the currents, in order to perform the automation functions on the system to increase reliability. So that's when you would, I don't know, connect the voltages to the recloser and not only the currents. Of course, there are reclosers out there that don't even have the voltage inputs, and in that case, you don't need to do that.
Okay. So Mike, could you please explain how to set the battery output to mimic the 52A contact of the Recloser?
Sure, let me go to that slide right quick. Let's see, here we go. Okay, so what you do is you need a source. So I'm using a battery simulator here, but it could be a substation battery. It could be a lot of things. The idea is to put an output contact. This contact is just a dry contact. It's isolated from the test set. It's controllable by the logic, so you want to series the contact, the input to the relay, and the voltage all together. So in this situation, you come out of the positive into the programmable contact, out of the contact, all the way over to the input, and then from the negative side of the input back to the negative of your battery source. The idea here is you're just needing a switched DC system right here. Every time input 1 is energized with 125 DC, the relay recognizes that as a 52A closure. If that DC is removed, then it recognizes it as a 52A open. I hope that explains your answer.
Thanks. So while we have you, what is the difference between reclose and restrike?
Reclose is when the reclosing relay tells the breaker or recloser to go closed, and it actually goes closed. If the fault is clear, then it's a successful reclose. If it is not clear, upon closing, upon a successful reclose of that breaker or recloser, the fault can restrike. So the difference in a reclose and a restrike, the reclose is talking about the breaker or recloser and the action that it's taking. The restrike is whether or not the arc actually reestablishes or not, whether the fault comes back.
Thanks. So our next question is going to be for Sughosh. Do some test templates exist for reclosing tests in the RTMS?
Yes. What we have is, like you already saw what Mike showed, we have the state sequencer feature that by default is set up for a two-shot lockout testing. And we also have these test templates that is embedded in the relay test plans. Based on the settings you read for the 79 element, it is going to automatically configure the template for your testing. So yes, we do have the templates.
Thanks a lot. While we have you, Sughosh, what is start and stop condition in state sequencer timing screen on the RTMS?
Yeah, okay, that's a good question. It's very important to understand the start and stop condition. So these conditions are nothing but utilized to decide when the timer starts for a particular state and it stops. So you can configure these timers to get your reclose times and trip times, and then you can decide the start and stop of each timers using these conditions. And these conditions can be started and stopped either by change of a state, or you can also do it using the change of a post. It can be a binary input operation.
All right, thanks a lot, Sughosh. And thank you all for attending. It looks like that's all the time we have for questions. We apologize if we didn't get to your question today, but we will be following up with you offline in the following weeks. But once again, thank you all for attending. If you could please remember to answer the survey. The survey will include a field for you to request a quote or a demo if you're interested. But I'd like to wrap it up by reminding everyone that we will have day 2 of this seminar tomorrow at the same times. Feel free to go register if you haven't already at us.megger.com/webinars. And I hope everyone has a wonderful rest of their day and, in fact, the week. Thank you all very much.